we've met, but I think people might watch this later on. So if I haven't met you, my name is Terry Surratt, and I am the work group lead for our process team here in Anchorage. And today I'm going to talk about some of our process team's capabilities and one of the kind of key tools, critical tools that we use in solving more complex problems. So when it comes to pinpointing bottlenecks and assessing equipment issues and design limitations, one of the critical tools we have to do that is dynamic and static process modeling. And it really has become, when it gets to the more complex problems, one of the go-to methods to help us solve some of those complex problems and answer questions about those complex problems. Now, that's not to say that every problem we encounter, every situation requires a complex simulation to solve it. You know, a single phase flow problem isn't really the situation where you're going to need to develop a complex model, but as the process gets more complex and the number of variables increase, a simulation really ends up saving us just countless hours. So first today, I want to talk a little bit about the capabilities of static and dynamic process simulations, kind of some of the advantages and just a little bit about the differences between them. And then I have a few case studies for us to go over tonight. The next slide, please. Process simulation for a specific project or to solve a specific question, and what questions we need to ask, you guys to help set that up. Next slide, please. So steady state versus dynamic state. So the steady state simulation is a snapshot in time. It's when you have a specific kind of basis to work to. So you have a set feed conditions, set material balance, set energy balance. And then once you have that set based on refinery data, you can use it to evaluate like a distinct step change. You're going to change typically one thing at a time and see how that impacts the rest of the steady state simulation. Some advantages to that would be that they're generally speaking quick and easy. They're built off of pre-existing kind of robust equations of state. So the simulation tools themselves already have kind of all the background molecular interactions and thermodynamics built in. So we don't have to worry about those calculations. It's really more about the assumptions that go into it, profiling like the data that we're going to feed into it. And then kind of the math behind it, that's all taken care of. So it's kind of bulletproof when it comes to that aspect, which feeds into the next point that it's reliable and reproducible. And the dynamic state, what we're looking at is a change over time. So we're really going to be looking at more real world scenarios. Think kind of what would happen if you do this? How is the downstream unit going to react to an upset at this point in the process? And so some advantages to that is that we can use it to, look at real world kind of operations and problems, and we can use it to a specific case would be to use it to determine actual relief loads versus more kind of point in time relief loads based off of like a steady state and kind of more traditional assumptions, which tend to be very conservative. Slide. So steady state simulations. I like to think of this as modifying the basis. We're going to have a set simulation on whatever existing basis and data, and then we're going to look at, like I said before, kind of a point change. We might modify the feed rate to look at throughput changes. We might modify the composition. We might want to look at a specific piece of equipment, which we'll look at in a case study I have in a second, where you want to modify some aspect of that heat exchanger or pump and see how that would impact the rest of the process. You can use it for hydraulic evaluation and debottlenecking. And one of the nice things about a simulation or steady state simulation is when you make that change to one piece of equipment, you can see how it works and cascades through the system. So if you're debottlenecking, you might have a limit at one point. Once you make that change, you can look at around there and see where that limit may or not have moved. I have a pretty good example of that in a second here. I'm actually going to steal the screen for a second, Terry, and pull up my example before I talk about dynamic. See if that works. Oh. I'm trying to share. That's me. That's me. There we go. Oh, okay. Slight technical difficulties. So this is just an example of a steady state simulation we did looking at the overhead of a distillation column. And the goal here was to look at overall hydraulics and assess changes in rate, potential changes to equipment, and potential changes to piping sizes, and how that would all play in together. And oftentimes what we'll do is we kind of set the basis with our flows and our composition. We might have a simple kind of test case to get an idea of the overall process. And then when we get down into the details, you can get pretty fine-tuned in modeling your piping and at specific points of the different line sizes and changes, in this case into an overhead condenser. And then the condensers themselves, you can use in HISIS specifically what's called EDR to model that in a lot of detail. And you can take the existing drawings of an air cooler, model it in for the two passes specifically, and all the little details. And then if you want to change any of those details, you can see how it results in a change to the overall hydraulic of the overhead system. One of the nice things about the static simulation, looking at specifically pressure drop, is you can just, once you have it set up, and it takes a bit of time to get the details set in, but once you have it set up, you can just quickly shift over and look at the pressure of each stream. So you can quickly kind of run through here and say, okay, well, this one right here, this segment of 18-inch piping, we have a little more than 2 pounds of drop. Our total drop here is about 8 pounds. And so we might be looking to increase that line size as an option to reduce that overall pressure drop. That would be one specific spot maybe to focus in as far as like a bottleneck when it comes to hydraulic losses. Let's go back to the PowerPoint real quick. In fact, since I have the screen, Terry, I'll maybe just keep the screen. We'll just do it this way, a little faster. So dynamic simulations. Like I said before, this is more of a kind of a what if. You can use it to look at the peak relief loads in the system, look at the impact of a unit upset in the overall operations. I've in the past used it to look at kind of more SIS related process safety time examples. Once again, it kind of all comes back to time. The dynamic simulation kind of does everything the static simulation does, but it does it with the integration over time. And so you can see if you close a valve, you can watch how the pressure changes at different spots in the process, or a vessel might overfill and how that affects the pressures up and downstream. So I have a quick example of that as well. And this specific example was it was a part of a relief study, and we were looking at a diesel hydrotreater, the reactor loop of a diesel hydrotreater that I have clouded here. It's just a cartoon I found on the internet. Most reactor loops are kind of designed in the same way. You have kind of your liquid feed and vapor feed from your compressor, and that's kind of your highest pressure in the system. And then your pressure drops as you go through your heat exchangers, reactor, and your separators, finally ending at your scrubber at the end of it, which is typically the lowest pressure in the system, and then the lowest design pressure in the system. And so what we were looking at was a few things. We were looking at the potential to overfill one of the separators. What would that hydraulic pressure look like if that vessel had overfilled? We were looking at what would be the settle out. So if you stop flow in and out, how does the pressure balance out in the system? And once you get the simulation built and kind of designed out, you can answer all of those questions with relatively small changes, and kind of get your answers out for a number of different questions, the same simulation. And so I don't have a live example of this one, but I just kind of wanted to roll through what the simulation kind of ended up looking like to do this. These are the high pressure, low pressure separators. You can model all this in quite a bit of detail in terms of level control, pressure control. And then I had just the settle out chart that that HISYS spits out. They're called strip charts in HISYS. You can plot any variable for any stream over time. And so this was looking at the settle out pressure at the lowest pressure piece of equipment in the system and just assessing if that settle out pressure would actually achieve overpressure or not, exceed the MAWP of the equipment. Then the last example I had, I just wanted to quickly run through. Oh boy, that kind of scrambled my desktop there. A quick dynamic example, if I can get it to run, of a test case or a problem looking at sizing a shutdown valve. This is for a well pad, produced fluids service. And in this particular service, we have a high low pressure interface. And at the high to low pressure interface, we have a shutdown valve. The intent of that being to close before we overpressure the downstream lower design pressure equipment. So the question was, how fast does that valve need to close before the downstream equipment can be overpressured? Fortunately, HISYS is not working too well for me. It'll work better this way. Yes. There we go. Okay. So one of the fun things about a simulation, or kind of the interesting things about a simulation, is you can simplify it so long as the assumptions you make are conservative assumptions. So in this case, the process itself is quite a bit more complicated than what I was looking at here, right? You have your different wells lined into the same header that you could be, you could also model those valves closing over time. You have different downstream valves that could fail closed. You could look at how long it takes those to close, and that could also be incorporated in this. But in this case, I wanted to distill it down to kind of the simplest question I could ask. And if I could prove that in this case, the valve will close in time to prevent overpressure, then in all those other cases with kind of less conservative assumptions, I can say that this valve would be, adequately sized. The closure time for this valve would be adequate. And so what we have here is just basically the header, however many feet it is, and our total kind of flow rate headed into the drill site for production. And kind of all you need to do once you have it set up is to close this downstream valve. So we'll set that to 0. And be able to watch as the integrator moves forward, and green is what we're going to watch here. Watch as the pressure climbs. So in this particular system, the downstream equipment is 300 class equipment. So we were looking for a design pressure limit of about 740. And so you can watch as the pressure climbs to about 740 in this case. You can rescale this to show that actual 740, but 745 is a good benchmark for that, right? So we can see where it crosses that, and we can look at how much time that took. And I mean, in this case, you have over a minute for that valve to close, which is a very comfortable time for a shutdown valve to have. So that's part of the specification that I pass over to the instrumentation team when they're speccing the valve. That's really all I have today. So you have any questions?
Well, so, you say a minute to close that valve, but you have to like look at the effects of water hammer, or well, was that gas?
It was 3-phase. Yeah.
Okay.
So in that case, so that's an interesting point, right? HISYS Dynamics doesn't really do too well with transient analysis. There are different programs. AFT Impulse is one of them that I would use for something more like a transient water hammer pressure spike. But when it comes to HISYS does really well with like 2-phase or 3-phase settle out pressures or pressure build kind of assessments. You can get those kind of settle out pressures or times, or in this case, the valve closure time, because the pressure doesn't spike like what you're kind of talking about with the transient water hammer effect. Just have Suji here. Do you have any more questions?
No. So in terms of time saving, how powerful is this tool versus more conventional ways of solving a process problem?
I would say well, of course it depends on the problem, but when it comes to anything that's multi-component, meaning it has more than one molecule in it, and when you start either vaporizing or condensing it, either you have to make so many assumptions that your answer is going to be incredibly conservative to do it by, because you can do all this stuff by hand. They did it by hand for a long time, but you have to make really simplifying assumptions to be able to do that. I'm not honestly sure how long it would take you to even just figure out, like here, let's take a really kind of simple example. As a process engineer, we do a lot of PSV sizing. One of the most common PSV sizing cases would be a fire case. To size a PSV, you have to be able to tell the instrumentation team and the vendor what's going through the PSV. So you take a fire case, take just a fluid that's going to vaporize. What's that vapor, right? If you don't have a good way of figuring out all of the properties of the molecules in that by hand, right? You'd have to go in and look at, okay, what component is this? What is the boiling point of this component? And then even in that, if you have, let's say you have half a dozen different components in that stream, they're going to interact with each other in a little bit of an odd way, right? And maybe change the answer a little bit. So you could figure out by hand at what temperature all those different things boil, and then what's their latent heat, meaning how much energy you need to boil a certain amount of them. And you could come up with that, but I mean, even just talking about it, certainly more than an order of magnitude more time. Yeah.
I don't disagree with that.
Yeah, it would take a long time to solve that problem by hand. And the HISYS, I mean, or Pro 2, 30 minutes. 30 minutes if you haven't done it before, right? So
Second question, if it's okay. No, I'm monopolized. Thinking of Alaska, you have upstream producers and then you have downstream refiners. Is there an application or some part of those clientele owners, operations that you couldn't use this tool for? Is there one limitation, I guess?
But I already spoke to the point of if the problem doesn't warrant a simulation, it's not worth the time to build one. But when it comes to, your simulation just not being able to answer something, simulation is really a tool to help you deal with kind of equations of state type problems. So, when are things going to vaporize or be liquid? It also is a great tool for hydraulics with multiple phases, right? The way we used to do that was to do the hydraulics kind of for the vapor and the liquid and then add it together, which isn't really how it works, especially when it comes to hydrocarbons, because depending on what pressure you're at, different components will be in the liquid phase versus vapor phase, like the kind of the lighting component. So it's just an oversimplification. But what could it not answer? So downstream, I have a pretty good answer for that. When it comes to like we're gonna get kind of specific here, but like when it comes to reactors, you can use Aspen Tech to do that, but you really have to know what you're doing and get into the actual reaction kinetics. Like most chemical engineers took one or more classes in college on reaction kinetics, like what each specific kind of molecule or really it's a change of how the molecules are going to change, how that's going to work and the energy in the system, and it gets really detailed. Often what happens is you'll have like a provider for a specific technology. Let's take like UOP, for example, and they have all that in the background. A lot of them have that kind of modeled. And I'm not sure what tool they use for that modeling, but they'll tell you, okay, if you feed in this, you're going to get out this. And then we do the HYSIS around that to do everything else, basically. So like specific reactions and reactors, I would say you can do it, but it's not something that we as a whole have a lot of experience in. It's really a real specialty type thing that you go to a provider. And another part of that is those providers like UOP is going to guarantee that performance. And so when you have a hydrotreater, and I'll look to you, when you have your hydrotreater, right? If it's not doing right, if it's making more LPG than you thought it was going to, you call your catalyst.
Yes, call it.
Yeah, right. You call your catalyst provider, and those are the people that build the models for how it should work. You don't call Anvil on, why isn't this reactor working? Like you said, you told me it was going to work, right? You told me I would get 2 years of functionality or however many years of functionality on this catalyst. So that's one thing in like kind of downstream. Upstream, not to be unappreciative of the complexities, but the process of the upstream is pretty simple relative to when you get into compared to like downstream processing. And so a lot of it is fluid flow and a little bit of separations, and all that can be done in HYSIS, including anything that has to do with like gas scrubbing and amine scrubbing. That can all be molded with HYSIS too, or Pro 2. I don't want to keep adding that. I just have more experience with HYSIS, so that's the name I drop more often. But really can do pretty much all of it. So,
Okay.
Yeah.
So it's a pretty powerful tool.
Absolutely. Okay, well, thank you.
Thanks.
Thanks for coming.